Hello friends, welcome back to my channel. I am available here with the new video related to heat transfer. In the last video we had discussed about critical radius of insulation and its numerical. If you want to know in detail about it, in the description box the link is given. Refer that video and you will get better idea about critical radius of insulation and numerical based on that. So in this video we are going to discuss about steady state heat transfer by means of conduction part 7, where we are going to discuss in brief about extended surfaces or fins. In the current video we are going to discuss about what is called extended surfaces or fins, what is the need to provide extended surfaces or fin, what are the different applications in the industry as well as in the real life where we will observe extended surfaces, as well as we are going to derive the most general equation for heat flow through rectangular fin. So friend, we come across lot many situations where in the very small area we have to transfer large amount of heat from the surface to surrounding. So whenever the available surface is found inadequate to transfer the required quantity of heat with available temperature drop and convection heat transfer coefficient, extended surface or fins are used. So these lines are talking about necessity of fins when we have to use the fin that is talked by this line. So here lot many situations available in which we have to transfer large amount of heat through small areas. So in the next slide we will go for different type of fin which is used in the industry as well as in real life application, that include straight fin, tapered fin, spines, annular fin as well as spin fins. Now we have to talk about what are the different application of extended surfaces or fins. So common applications are cooling of electronics component, condenser and economizer of thermal power plant, dry type of cooling towers, air cooled cylinders of compressor as well as of IC engine, evaporators and condenser of refrigeration and air conditioning system, electric motors and transformer, etc. So these are some applications where extended surfaces or fins are used to enhance heat transfer. In the current video we are going to discuss about determination of temperature distribution and heat flow from different type of fins. The knowledge of temperature distribution is necessary for their optimum design with regards to size and weight. So now friend, we try to derive the most general equation for heat flow through rectangular fin. In the figure number 28 you can see the rectangular fin is available which is attached with the wall. The nomenclature related to fin are shown in the figure number 28, which indicate that T0, that is the base temperature of the fin in terms of degree Celsius, T is the temperature of the surface in degree Celsius, K, that is the thermal conductivity of fin material in watt per meter degree Celsius, H is the convection heat transfer coefficient of surrounding fluid in watt per meter square degree Celsius, TA, that is air temperature or you can say ambient temperature in degree Celsius, L is the length of fin, that is protruded length in terms of meter, Y is the thickness of fin, B, that is the width of fin, P, that is the parameter of fin, that is 2 into bracket B plus Y, unit is meter, and ACS, that is the cross section area of the fin, that is area perpendicular to the flow of heat, that is B into Y, unit is meter square. So all the nomenclature related to the figure number 28 about fin, about rectangular fin is shown here, what we had discussed. Now, for analysis of heat flow from a rectangular fin, following assumptions are made. First, you can say steady state heat conduction without internal heat generation, one-dimensional heat transfer, uniform convective heat transfer coefficient over the fin surface, contact thermal resistance is negligible, homogeneous and isotropic fin material, and heat transfer by radiation is negligible, and the thickness of fin is very small compared to the length and width, so the temperature gradient over the cross section are negligible or neglected. So I hope this much things are very much clear to you, and now we are going to derive the motional equation for a rectangular fin. For that we are starting with consideration of heat flow at a distance x from the base having the thickness dx in positive x direction. So you can say heat conducted in the element at a plane x, that is qx, that is equals to minus ka dt by dx according to the Fourier's law, and we'll get q of x plus dx at the thickness dx, that is equals to minus ka into dt by dx at x plus dx distance. Plus we know that the heat convection takes place from the fin to the surrounding, and that value is Q convection, that is equals to HA delta T, that is HA into T minus TA, where A is the perimeter into dx distance into H into T, that is the temperature, minus TA, that is the ambient air temperature or ambient temperature. So we can say that Q, that is equals to Q of x plus dx plus Q convection, that is heat which is coming from the base or heat which is coming from the hot body, that is dissipated into the surrounding by means of convection, plus it is transferred into the fin by means of conduction. So Qx, that is equals to Qx plus dx plus Q convection, and if we will write in terms of Fourier's law and Newton's law of cooling, you can say Qx, that is equals to minus Ka dt by dx at x, that is equals to Q of x plus dx, that is equals to minus Ka dt by dx at x plus dx distance, plus Q convection, that is H into area, that is perimeter into dx into temperature difference T minus Ta. So I hope last equation number 36 is very much clear to you. That is heat transfer from the body to the fin and to the surrounding, that is Qx, that is equals to Q of x plus dx plus Q convection. So if we expand the dt by dx at x plus dx according to the Taylor's expansion series, which we learn in maths, we have dt by dx at x plus dx, that is equals to dt by dx at x plus d by dx of dt by dx at x into dx plus d square upon dx square into dt by dx into bracket dx square divided by 2 factorial bracket complete plus so on. So if we'll consider dx is towards 0, that is dx tends to 0, in that case we can neglect higher order terms and we will get dt by dx at x plus dx, that is equals to dt by dx at x plus, you can say d by dx of dt by dx into x plus dx. So we are considering first two terms only, and all the higher order terms we are neglecting. So we will get equation number 36, we will get minus ka dt by dx into x, that is equals to minus ka dt by dx at x minus ka d square d by dx square into 8x into dx plus h into area, that is p dx into t minus ta. So from both the side, minus Ka dt by dx at x distance is common and that will be cancelled out. So we will get Ka d square t by dx square at distance x into dx, that is equals to h into p dx into t minus ta. Now if we will divide on both the side by cross section area into dx, we will get k d square t by dx square minus h into p divided by cross section area into t minus ta, that is equals to 0, or we can rewrite in the form of equation number 37, that is d square t by dx square minus ph divided by ak into t minus ta equals to 0. So if we want to simplify this equation number 37, we are defining the new term that is called temperature axis theta. So the temperature axis theta is equals to T minus TA. So if I will write theta x, then it is equals to Tx minus Ta. Now instead of theta, if I will write theta 0, then my equation T minus Ta will reduce to T0 minus Ta. So temperature axis theta is equals to T minus Ta, and if I will go for differentiation of this d theta by dx, I will get dt minus dx, and upon second differentiation I will get d square theta by dx square, that is equals to d square t by dx square. So if I will write these values in equation number 37, I will get d square theta by dx square minus m square theta, that is equals to 0, where very important term is available with us, that is called m, that is called Finn constant, that is equals to under root of pH divided by ak, that is perimeter, into convection heat transfer coefficient divided by cross section area of the fin, and K, that is the thermal conductivity of fin material, and unit of M, that is fin coefficient, is 1 upon meter, or you can say it is a meter inverse. So in the competitive examination the question may be there, what is unit of fin constant? So it is meter inverse. So now equation number 38 which is available with us, that is d square theta by dx square into m square theta, that is equals to 0, where m is the Finn constant and its value is under root of pH divided by ak. Now equation number 37 and 38 are general form of heat dissipation via extended surfaces to the surrounding, and the solution of above linear and homogeneous second order differential equation which we learn in maths is theta, that is equals to C1 e raised to mx plus C2 e raised to minus mx, where theta, that is equals to T minus Ta, that is equals to C1 e raised to mx plus C2 e raised to minus mx, where Ta, that is ambient temperature, m is a Finn constant, C1 and C2 are constant, and that values are available by putting proper boundary conditions. So the very first boundary condition which is known to us is when x equals to 0, temperature equals to base temperature T0. So at distance x equals to 0, temperature is equals to base temperature. So when we will put that values in equation number 39, we will get T0 minus Ta, that is equals to C1 e raised to m into 0 plus C2 e raised to minus m into 0. So we will get theta 0, that is equals to T0 minus Ta, that is equals to C1 plus C2. This is the one common boundary condition which is available for a rectangular fin with boundary condition x equals to 0, at that time temperature is equals to base temperature. Now the second boundary condition is available depending upon the type of application. So you can say, if we consider the case 1, then the fin is very long or fin is infinitely long and the temperature at the fin tip approaches that of the surrounding temperature. Second case, that is, fin is a long fin with negligible heat loss from the fin tip. If we'll consider the third case, then the finite long fin with convection heat loss from the fin tip. And the last case is the finite long fin with specified temperature at its fin tip. So these are 4 different cases for a rectangular fin for which second boundary condition is available, and when both the boundary conditions are available, we can solve this equation and we can find out what is the heat is transferred from the fin to the surrounding plus what is the temperature variation in that particular cases. This is about the case 1, 2, 3, 4 and the most general equation for extended surfaces. So friend, in this video we had discussed about what is called extended surfaces or what is called fin, where we have to use the fin or where we have to use the extended surfaces, what are the different application of fin in real life as well as in industrial application, and we had discussed about heat flow through rectangular fin, where we will get the most general equation, that is equation number 37 and 38, and when we try to find out solution of that equation with boundary condition, we are having one particular boundary condition, and for second boundary condition we have to select what is the particular type of fin, whether it is the infinite long fin or whether it is a fin with finite length and fin tip is insulated, or whether fin is of finite length and tip of the fin is not insulated. So if you like this channel, do not forget to subscribe this channel and share this channel among your friends. Thank you. Have a nice day. Goodbye.